Cool. I've got my trusty assistant here. You can't really see him, but we're gonna Chuck and I are gonna teach you about polyatomic ions, right? This is just more nomenclature kind of stuff. This is rules from the IU pack as we come up. So I want to dive into polyatomic ions and what that means for us and how we're gonna do stuff. Uh, there we go. Okay, so essentially, right, all the ionic stuff we've talked about so far has been a monatomic ion, meaning that it has a single atom involved with it. Polyatomic ions have more than one atom, right? As that makes sense, I guess, based on the name. Um, and we can think of this as just a molecule that has gained or lost some electrons. Okay. Chemically, now the important part here, chemically, these behave as a single unit. Okay. So when we're thinking about doing formulas and we start doing reactions and stuff like that, the fact that the polyatomic ion will stay together and act as one thing is going to be very important for us. Okay. So part of our goal is going to be, can we recognize polyatomic ions, right? And then we're going to dive into, can we name the polyatomic ions and then name compounds that contain polyatomic ions? Okay. The nice thing is the rules for naming the compounds are the same as the rules for naming binary compounds, right? So we're going to be able to have a cation name and an anion name, put them together and make the name of the ionic compound, okay? All we're going to need to know is think about and stress, where am I at? Okay, and stress about how to deal with the formulas, okay? Uh, and all that stuff and the names of the ions themselves, right? So we can recognize these things, right? They'll have more than one atom, but they'll have a charge. So this is a positively charged one. We can have, say, SO4 2 minus. That's a nice negatively charged one. We could have PO4 3 minus, or say ClO3 minus, right? These are all good polyatomic ions, okay? Um, when we're writing formulas of compounds with these things, we'll treat them exactly the same way. So like if we had an NH4 and a Cl minus, let me write this out instead of just saying it, NH4 and a Cl minus, these guys will make a compound together, NH4Cl, okay? One of those and one of those, okay? If we, however, pair the NH4 plus with something with a 2 minus charge, like sulfide, sorry, um, then we'll need to have two of the NH4s. And to do that, since there's already a 4 there, we're going to have to put that in parentheses. This just means that we have two of that NH4 unit, and we have one sulfur to go with it. Okay. If you don't have the parentheses there, then it's at 1 nitrogen and 42 hydrogens, and that just is redonkulous. Okay. We'll do one more here. Okay. Let's say we had a calcium that's a 2 plus, and we're going to use PO4 3 minus. Okay. This is another example of a 2 and a 3. We can do this switcheroo, right? The 2 should go here and the 3 should go there. So we can come up with a formula that's going to have 3 calciums and then 2 PO4s. And again, we need parentheses because that's 2 of the PO4, not 1P and 42 oxygens. Okay. We can think of this, and it might make it a little bit simpler when we're learning to do this. You can think of this since the PO4 acts as one unit, that you have a Ca2 plus, and you just have X3 minus. Okay. In which case, you could turn this into a formula by saying Ca3X2, and then you can substitute PO4 for X to get the actual formula back. Okay. Both of these things are going to work as we go. All right, let's dive into naming so we don't have to say PO4 or SO4 all the time. We can start using names of stuff. All right. Um, yeah, there's a ton of these. There are probably, I don't know, I was going to say millions, at least thousands of polyatomic ions. I'm not going to make us know all of them. I'm going to give us there's a list, and I want you to know the list. The list is on Blackboard. You'll get a handout in class, so we're not going to stress too terribly about it. You can brute force memorize every single one of those, and you'll be fine, okay? I like to memorize less and learn based on patterns. So I'm going to show you the patterns of the names And then once you know the pattern, you can come up with all kinds of stuff. Okay. Once you know the patterns, you can come up with names of polyatomic ions uh, that you find in the wild that aren't necessarily ones that I forced you to know, but you can kind of derive what their name should be. So uh, let's take a stab at this. We're gonna start off with some patterns. Most of these are anions, and there's very few of them that are cations. So cation ones are these guys. Ammonium, that's our NH4 that we just talked about. Hydronium, H3O plus, and mercury 1. Mercury 1 is weird because how you're saying it's mercury 1, there's a parentheses there. Why is there a 2 plus? Well, it's because this is really two mercury 1 pluses that are stuck together. Okay. It doesn't happen all the time. Well, I mean, it happens all the time for this thing, but it's not a very common one for us to see, especially in lab. We're not gonna do anything with mercury in lab. Anyway, those are the three positive ones. Everything else is a negatively charged one. Um, we're gonna go through these as we go. Okay, so our basic rule is most of these are called oxoanions, which means that they have some element and a bunch of oxygens and a negative charge. Okay, we can figure that out. And one way we can start to recognize polyatomic ions is because they either have an ATE ending for their name or an ITE ending for their name. Okay, all of our oxoanions are going to have either ATE or ITE. Now, the nomenclature rule is that the most common one has ATE, and if you have less oxygen, it's ITE. So we can kind of see the patterns here, right? Here's NO3 minus being nitrate, NO2 minus being nitrite, because we've lost an oxygen to do that. Okay, SO4 sulfate, SO3 sulfite. There's a few on here that don't have the ITE versions, right? Carbonate does not have a carbonite version. These other ones are kind of weird other examples, but these are ones that we're going to encounter and be able to deal with, right? Phosphate becomes phosphite. Okay. Once we have that down, there are some weird ones. And again, we say transition metals are weird. I say halogens are weird. We got weird all over the place. Okay. Halogens are weird because they can have multiple polyatomic ions, right? So if we have ClO3, this is chlorate. ClO2 minus is chlorite. That follows the pattern we just saw. However, you can also have ClO4 minus and ClO minus. Okay, ClO4 will be perchlorate and ClO minus will be hypochlorite. Okay, so we're going to add per if there's more oxygens than ATE, and we're going to add hypo if there's fewer oxygens than ITE. And all of the halogens do this, chlorine, bromine, and iodine, and they all follow the same pattern. So once we have that, there's another set of polyatomics here that we can grab. There are other things that do this, but we're just going to focus on the halogen ones as we do that. Okay, another thing we can do is these oxoanions can pick up an H plus from somewhere. This is acid-base chemistry, and we'll see this as we do some stuff later on too. Okay, so while carbonate doesn't have an ITE version, carbonate can pick up a hydrogen to become hydrogen carbonate. We just tack the name hydrogen on the front. So these are technically acid-base reactions, but so we have CO3 2 minus, and we're going to add an H plus to it. So this becomes HCO3 minus. Notice that the total charge is the same, right? The CO3 is a 2 minus, the H is a positive, so this becomes 1 minus for the HCO3. Okay. There we go. This one also has a common name. You've probably heard of bicarbonate, sodium bicarbonate, for example. This is household baking soda. We'll use that in the lab all the time. But bicarbonate is still used. Sometimes you hear people say bisulfite, but that's falling out of favor for hydrogen sulfite. There's one that's not on here that I could probably tack on here would be hydrogen phosphate, which would be HPO4 2 minus. Because phosphate has a 3 minus charge, you can add one hydrogen and get hydrogen phosphate, or you could add 2 hydrogens and get dihydrogen phosphate. This is the only time we're going to have a prefix in an ionic compound is because of the di for dihydrogen phosphate. Okay, you could do these with the phosphites as well. So again, this opens up a lot of naming conventions as we go. Okay. Another one, this is slightly less known, but there's an idea of if you replace an oxygen on the original anion with sulfur, you can add the prefix thio to it. So if we take sulfate, which is SO4 2 minus, and substitute in an oxygen with a sulfur, you get thiosulfate. This is literally the same color as that. That's funny. Okay, sorry. Where was I going? Right, so a sulfate, and we'll get into what these look like later on, but a sulfate looks like this, right? There's a minus charge there and a minus charge there. Um, thiosulfate, we've subbed out one of those oxygens. So thiosulfate would be this. Actually, it's probably a double bond on the S. Right, and we're not going to stress about how to draw these things at the moment. We'll get into that later. We're focusing on names. I went on a sidetrack. Okay, yeah. This one is, we will often work with thiocyanate more than we work with cyanate, just because it's more common, and it's a little bit more stable. But again, the naming convention is still there. Cyanate becomes thiocyanate. There's a bunch of oxoanions that come from organic chemistry names. This is because these are related to organic acids, and we're not going to go there. But for these ones, oh shoot, I don't know what I did. Okay, sorry, brain. Okay, so acetate is probably a very important one for us to know. And acetate can be written lots of different ways depending on where you see it or how you see it. I frequently will focus on this one, C2H3O2 minus, but I know for a fact you will see these other ones other places, like in the homework or maybe on an exam or something. You might see those other ones. So get used to all of those. And then this is oxalate, C2O4 2 minus, not to get confused with CO3 2 minus. So just, yeah, whatever. Okay. Some polyatomic ions are named like monatomic ions, and that is just unfortunate for us. And that last one I did, we talked about cyanide. Cyanide is Cn minus. All of these have IDE endings, so they're kind of masquerading as monatomic ions. Azide N3 minus. More often, hydroxide and cyanide are the ones we're going to see all the time. But I'm throwing these other ones at us here too: peroxide, superoxide, and azide. Just to start recognizing those things. Okay. When we're writing the names of compounds, we just want to be able to say what the name is, right? It's anion, cation name, and then the anion name, and we already just saw all those. You'll be armed with a list of those for practicing, but you won't get to do that for the exam, but you know how we're gonna do this. So, okay, break it up. CrO4, that's our polyatomic, that's our negative, that's chromate. Okay, this has a 2 minus. Remember, lead has options. So if we know this is 2 minus, then this lead has to be 2 plus. So then this is lead 2 chromate. Okay. We can do the same business over here with this guy. Notice we have the parentheses here. There's our SO4. This is sulfate. Okay. Remember, sulfate is 2 minus, which means this chromium must be 3 plus because we have 2 and 3. This is a reverse switcheroo. Since this is 3 plus, this is chromium 3 sulfate. Okay. We'll come down here. We have this guy. Here's a polyatomic PO4. Remember, PO4 is 3 minus. So again, if there's 2 PO4s that are 3 minus, this mercury has to be a plus 2. So this is spelled weird because I can't write mercury 2 phosphate. Okay. Last one we're gonna get here. Hopefully you recognize this dude. Looks mildly familiar, right? There's our acetate. Right, acetate is 1 minus, so the barium here has to be 2 plus because we have 2 acetates here. Barium doesn't have options, so we don't need the Roman numeral, so we're just gonna say this is barium acetate. Okay. Again, if you can do it forwards, you can do it backwards. So let's do these. Again, the name tells us what the ions are. We just have to put them together. And so as we're starting this off, you'll probably want to write the individual ions and then you can twist it into a formula because that's probably the easiest way to do it. Iron 3 phosphate. So remember, it tells you the charge. So that's iron 3 plus. Phosphate is PO4 3 minus. So these two together become FePO4. Straightforward. Titanium 4 oxide. So Ti for titanium. This is a 4 plus. Oxide is a 2 minus. Okay. This isn't a polyatomic ion. It's just a weird example. Okay. If we do the switcheroo, we're going to get Ti2O4. That is super wrong, although you're close, but it's super wrong because we don't want to have that. We want to have the lowest whole numbers possible. So since that's reducible, this is TiO2. Okay. Manganese 3 sulfate. So manganese 3 plus. We know a sulfate should be SO4 2 minus. We got a 3 and a 2, so this should be manganese 2 there. Sulfate would need our parentheses. 3. Okay. Potassium hydrogen sulfide. Okay, these, I don't know why I'm doing that. Okay, these are going to throw us off. Potassium, there we go, is the front. Remember, potassium is always going to be K+. Then hydrogen sulfide is the other piece. Remember, sulfite is SO3. Hydrogen sulfide would be HSO3. And so this has a minus charge. So this is KHSO3. Okay. One last on here, tin 4 chlorate. Remember, tin is not Ti, that's titanium. This is SN4 plus, and chlorate is ClO3 minus. This will become really straightforward once you get those polyatomics memorized. We need 4 chlorate, so we have to have our parentheses there, right? Make some flashcards, ask questions as needed, practice, practice. Practice is the only way we're going to get better at this, okay? Let me know if you need me, and I'll catch you later.